Hi, my name's Deborah Fowler. I've been using trigonometry for years and thought that an overview of the basic principles might be helpful for those less familiar. I'll also be using Houdini during this demonstration. So let's first talk about right-angled triangles. Right here I have a triangle and it has a 90-degree angle, which makes it a right-angled triangle. There are two sides, which one of them is closest to the angle, which we call the adjacent side. The one that is opposite the angle is opposite, and the longest side is called the hypotenuse. So just to add some labels, the properties of the right triangle look like this. So what can we do with this? Well, there are certain properties that exist. So you might remember these from high school. Cosine of angle is adjacent over the hypotenuse. The sine of the angle is the opposite over the hypotenuse. And the tangent of the angle is the opposite over the adjacent. We're going to mostly use this one today. Well, often in procedural animation, what we're looking for is the angle. So if we take the inverse function and take that on both sides, what we get is the angle with an expression that uses the inverse function of each of those trigonometric functions. So for example, here, if we take the inverse function of cosine on both sides, we get arc cos of adjacent over hypotenuse, and then angle is simply left. So what we have is the angle is equal to the arc cos of adjacent over hypotenuse, sine and tan in the same manner. So this gives us ways to compute this angle. It also works with the other angle, except now that the roles are reversed in that the adjacent is the green segment and the opposite from this angle is the purple segment. So how does this help us in animation? Well, let's take a look in Houdini. So in here what I've done is, rather than being theoretical, I've decided to create points, specific points in space. So I have 3 points that I arbitrarily chose, and these points are defining a triangle. These are also a right-angled triangle, and I'm determining the angle based on these points. So this angle here. How do I do that? Well, I use those principles that we just covered. So I'm just going to go back here. You can see that I have specific points that I'm referencing. So for example, the opposite side is simply the difference between the y-coordinates. So if we take 0.5 and subtract negative 0.5, we get 1. So the length of this segment is 1. If we look at the adjacent, if we take 0.8 and subtract off minus 1.0, that becomes an addition, and we get 1.8. So we now know the lengths of these two sides. Well, if you recall from our equations, that's the opposite over adjacent. So this angle would then be calculated by the arctan. So what that gives us then is arctan is opposite over adjacent, or in other words, arctan is 1 divided by 1.8. So it doesn't really matter where these points are. You can see that that angle is still being calculated. So how does that work? Well, what we're doing is we're just calculating a number to give us that value. So if I dive inside here, and ignoring all the labeling, what I've done is I've set this up so that I can reference points, point 0, point 1, point 2, and then I've created a line segment between those 2 points and colored them various different colors corresponding to my diagram. And then I've merged those together so that you can see over here I have a circle which I'm calculating that value specifically based on the differences in the point values. So in other words, the difference in y and the difference in x. So if I bring up the labels again, there we go, you can see that what I'm doing is taking the y value of 0.2, subtracting off the y value of 0.1, and that becomes my numerator. My denominator is just the x value of 0.1 minus the x value of 0.0, which is my denominator, Well, that's just opposite over adjacent. In other words, in this case, 1 over 1.8. And I take the arctan, which gives me the angle. And that's exactly what I'm displaying. In this case, 29.0546. But if I move these around, of course, that value will change. So that gives us a very handy way of defining an angle. So where could we use this? Well, let's take a look at a specific example. So in here, we have a set of wings, if you will. Could be a butterfly, could be a moth, could be a dragon. But what's happening is it's being pushed by this post. So how in the world do we do that? Well, we're using the exact same definition. So if I dive inside here, if you take a look at this, this is just a tube. So the tube is moving up and down based on some expression. This expression is just, in this case, I used a sine curve. So I said sine times the frame number times 10 to speed it up, times the amplitude, or in other words, the amount that it goes up and down. So this is going to go up 0.4, down 0.4. So it's just moving up and down, up and down, up and down. Over here, what I have is a circle, which I have reduced to 3 points, polyextruded it, and colored it purple. And in here, what I'm doing is I'm calculating the expression based on arctan. So in other words, I'm taking the y value, which is going to be the amount of the maximum y value of the stick, in this case, and where that stick is located in x, which happens to be, in this case, the center point of that stick, so that we get our motion. I've also mirrored the wings so that we could see it on the other side. So if you look at this in annotated form, what we get is the wing moving up and down based on the angle that we're calculating, based on the distance that the tube is away from the center and the amount that it is in y. So in other words, from this blue origin line or this red origin line, the x-axis, to the y max. So that gives us the angle based on those right-angled triangle relationships. So keep in mind that this relationship is 2D, but your object is 3D. So if I look at my object in here, you can see that it's three-dimensional, and I chose for my wings just to be a circle with 3 divisions. So it could be any shape. So the relationship is planar, but the object itself is 3D. Well, this could be done whether it's moving up or down. So again, we have that same triangle relationship. Again, we could also add movement to that center point. So what I'm doing here is very similar, except that now our center point is moving, and I happen to move that using a cosine. So this is a sine, this is a cosine. I'm just taking the difference. So if I stop this for a moment, and let's just scooch to right here, say, the difference between the maximum value of the stick from that center stick is going to be the height of this side, which is our opposite. Our distance to that stick is still the same, just that distance that we've moved the stick, and we calculate our angle using opposite over adjacent. So if I look at the expression that I'm using in here, let's just go over there. Take a look. You can see that we're taking the maximum value of the stick, subtracting off the maximum value, or the y max, of the center stick, and then dividing by the x value. And then when we take the arctan, it gives us the angle. What I'm doing over here is just simply transforming the wing, which is sitting at the origin normally, up to the center stick value. So in other words, this is calculating how much it rotates, this is calculating the position that it should be in. So we now have flapping wings. So that's a practical way of using arctan.